Hello. Hey, what's up, everyone? Happy to be here today. Hope everyone's having a good conference so far, good Denver. Hopefully it's not freezing everyone's asses off just yet. Thanks for the Axelar team for having me out here and telling you guys what is something that I'm personally really excited about talking about, which is basically the trust spectrum of the interoperability problem. And I'm going to be talking about that, kind of the spectrum in which we see a lot of different solutions, thinking about trust and the trade-offs inherent for connecting two disparate domains together in a cross-chain communication protocol, as well as I'm going to share a little bit about what I personally think is the end state for the entire space. And so excited to kind of unveil that for you guys today. And so a little bit before that, I just want to give a quick introduction of who I am and why it matters that I'm here today and telling you guys about about the interoperability spectrum. But my name is Jim. I've been in crypto for about 5 years. Most recently was at Aave, leading experiments there. Now I'm building a new cross-chain project called Catalyst, which we'll be announcing at ETH Denver on Saturday. So a little bit of alpha for you guys. But we'll be kind of keeping a little bit mum and telling you guys a little bit more of a broader vision that we guys have at Catalyst, which is just thinking about the interoperability problem really deeply. And so interoperability is hard. I think most people in the space who are here today know that it's hard. There's a lot of different factors that we have to think about at play when we think about connecting two inherently distrustful domains together, whether it's asset bridging or whether it's passing arbitrary messages. And so exploits is something that we've seen, and I don't want to rehash. I'm sure many folks at this conference have been talking about that already. Incompatibility, as you think about different virtual machines, different languages, different schemas that exist on different domains, like Ethereum versus Cosmos, for example. And it's complex. You know, a lot of this technology is being built as we speak. A lot of new kind of foundations are still being developed in R&D labs, and so definitely a very emergent space that I'm personally very excited about and have been excited about for the past few years. And so cross-chain is hard, and I think the number one thing that people think about when they want to solve cross-chain is very much how do you make cross-chain safe? I think the panelists before were kind of thinking about what does it mean to have cross-chain be inherently safe. And it turns out everyone wants to do that, but it's a spectrum. It's a spectrum of how you're actually able to accomplish that. And with that spectrum, you kind of have a trade-off. And so this is something that I wrote in a piece last month of what I think that interoperability spectrum is. But basically on one side, you have humans. You know, you're trusting humans and reputation and the entities and legal structures that we have in the meat space in order to allow for that safety. But the second part, on the other end of the spectrum, you have machines. You trust code, you trust kind of the trustlessness of code in order to actually enable inherent security properties between two distrustful domains. And so you can see that there's kind of a spectrum that lies between those two polar ends. And so with that spectrum comes a trade-off. And so when you want to say, I want to have safety, you're also inherently thinking about what does it mean for this trade-off that you have. So on one end of the spectrum, if you're trusting humans, you're inherently being more extensible, as some of my colleagues have said. Or how I like to frame it, you're having quicker time to market. And in a world in which you have all sorts of different domains with different virtual machines and schemas, it's actually much easier to rely on humans in order to expand into these new domains, and therefore they are extensible. On the other hand of the spectrum, you're solving for pure trustless security when you're trusting machines. And that is something that other kind of solutions have tried to solve for. But what comes with that is a research into more kind of nascent technologies as it pertains to ZK snarks and other kind of nascent developing R&D primitives in order to provide that trustlessness. And so again, kind of the trade-off is you could be here now, trusting humans into all sorts of domains, or you could be here in 5 years, trusting no one, and it's really great, but 5 years away. And so that's something that is something that many companies and many projects in their space really have to deal with when they're thinking about the interoperability problem. And so when you see in this spectrum, you can kind of categorize the two solutions into two different buckets. And so inherently, what every solution is trying to do is verifying messages. When you're passing one message from a domain and you're saying it to another one, you want to make sure that it's correct. Because if it's not correct, you're going to have a problem, as we've seen with a few other projects in the past. And so how do you actually verify that is two different buckets. One bucket is off-chain verification. So you're basically running a phone node, or you're having a committee of people running a phone node in order to verify the validity of one transaction in an origin chain. And you're submitting that transaction knowing that it's correct on a destination chain. The other end of the spectrum on a different bucket is on-chain verification, where instead of relying on off-chain actors, you basically have the destination chain have mechanisms in place in order to actually verify the validity of a transaction on the origin chain. And so we call that on-chain verification. And so if you plot all the different projects in the space along this spectrum, you can kind of see that a lot of them are falling kind of in that middle bucket, right? They're saying, I'm not fully trusting one entity in order to have a very extensible design, but I'm not fully trusting kind of the code primitives or the cryptographic primitives that we have in place in order to enable that, because that just takes too long, and I can't be in different domains very quickly. And so that's kind of the spectrum and the trade-off that we see for all these interoperability projects. And so kind of double-clicking into what each of these different spectrums are very quickly, I'm sure many folks are quite familiar with kind of this implementation, which is a multi-signature. And so instead of trusting one entity in order to verify a message, such like CCTP and Circle, you're actually trusting a committee. And this is what I like to call the OG approach to bridging. Because essentially what you have is a committee of folks that have a N of M, a kind of threshold signature scheme in order to validate a transaction is correct. And so instead of saying, oh, yes, like one person needs to just run a full node and see that this transaction is valid, it's going to be a committee of 5, 15, 25. We've seen various number of implementations. And there needs to be some sort of threshold, whether it's a majority or whether it's even a 2/3 of people voting on the validity of a state and actually passing that through into a message. So this is something that is quite frankly a very, very quick time-to-market solution that we've seen a lot of implementations kind of deploy. Kind of more recently, that's been really popular in the past year, is more of a coordination approach. And so this is something that is known to be, at least for now, an optimistic verification. And so instead of relying on a committee of folks signing, you're essentially breaking the job of bridging the two different jobs. And so you have a relayer that is passing a message optimistically, basically, but you have another actor called a watcher that's essentially monitoring these optimistically passed messages, ensuring the validity of them. Not saying that the relayers don't also kind of have some validity assumptions or validity kind of mechanisms in place as well. But essentially, there's this challenge period that is happening. And so it could be 1 hour, 4 hours, 1 day, what have you. But within that period, the watchers are going to be looking at all the relayed packets and ensuring they're valid. And so this is something that has a little bit more trustlessness in it because it's an honest minority one-of-n trust assumption. So you just trust that there's at least one good watcher acting and looking into the relayed packets. But again, it's a little bit less extensible than what we've seen with the multi-signature approach. The next approach that is, again, more trustless is native verification. And so essentially what this means is instead of having any sort of off-chain actor, you actually have two chains that are interacting in this cross-chain transaction flow, verifying one another. And so how that actually happens is with these chains running like clients of each other, which kind of at a high-level kind of view of it essentially means that each chain is participating in the consensus of another chain. And so they're able to see when the actual native verification mechanism of the origin chain is completed, and therefore they know with certainty that it is a valid transaction that could be executed upon on the destination chain. And so this is something that we call a trust minimize approach, because you're essentially trusting only the inherent chains that are involved in this process. You're not inheriting more trust assumptions from an off-chain actor. But it's still not, I would say, the holy grail or the most trusted solution in the space, because there is an assumption in place called an honest majority trust assumption, which basically means that you are trusting that all the nodes of the participating parties are actually being truthful. And so there is an instance in which a native verification mechanism could be exploited, in which the origin chain's validators are actually signing a side block or an uncle block that isn't actually being passed into the kind of main chain from a fork choice rule perspective, and therefore they're kind of attacking the destination chain, but kind of lying and obfuscating the fact that even though they all signed for a valid transaction, it's not actually the real transaction on the origin chain, and therefore the destination chain can act upon it, and that might actually economically hurt them. And so teams have come out and said that this is not necessarily the best solution either. And so I think what is very nascent in the space is the idea of using snarks, which is a combination of external and native verification. And so instead of having kind of the very inextensible design of the previous case of light clients verifying one another, which is really difficult when you look at, n number of chains and all these chains need to run like all sorts of different light clients. You actually rely on an off-chain actor, in this case, a ZK snark prover, in order to actually perform those transactions. And so in this flow, there is a off-chain verification from an entity running a phone node on the origin chain. They're actually generating a snark against that verification, sending that to the destination chain, and there they can actually verify that the snark is valid on chain. And again, this is something that is more scalable, but still relies on the honest majority trust assumption that we talked about in the previous case. Because again, you're still relying on the inherent proof of consensus and the honest kind of majority assumptions of the origin destination chains that are interacting with one another. And so the absolute holy grail of trustlessness is rollups or canonical bridges. And they're the most secure because they do something called proof of execution, where you actually have a proof of a state transition. And so in this case, validators of the L1 actually verify the validity of the new state root of the rollups. And so if you think about something like an Arbitrum, where they're posting kind of the state of the transactions in which they're compressing onto L1, Ethereum is actually verifying the validity of the data availability as well as the fault proofs in order to actually have kind of verification of that what happened on optimism actually took place. And so this is something that we call an honest full node, a single honest full node assumption, which basically in the case of Ethereum, you're just assuming that there's one honest full node on Ethereum, which is a pretty easy trust assumption to make. And so this is the most trustless of all, but as you can probably tell, this is only pertinent for a rollup to L1 experience. And so this only works for optimism to Ethereum, or another rollup onto a Cosmos settlement layer, for example. But it would not work in terms of extensibility, and it would not work in terms of going to time to market as you want to expand to different places. And so this does not work for something like an Avalanche to a Polygon because they're not rollups of each other. And so I kind of walk through the different solutions in space, and you're seeing that as we move slowly on the right-hand side of the spectrum, you're sacrificing a lot of extensibility, and you're sacrificing a lot of time to market, and you're kind of relying on a mechanism that is either not extensible or takes a very long time in order to actually expand to different domains. And so that's kind of, I think, up until this point, the inherent trade-off that every interoperability protocol has made. But I'm here to present you guys today something that I don't think I've seen many people talk about, which is bringing modularity actually into the interoperability thesis. And so folks are kind of familiar with the modular blockchain thesis. I'm presenting the modular interop thesis. And so essentially what we're doing is we're breaking apart the idea of what a cross-chain interoperability protocol does into 3 different pieces. And so you can see here its application, which is kind of inheriting application-specific standards from the level, something like queries, cross-chain, or cross-chain accounts using account abstraction. You have kind of verification, which is the ability to actually verify the transactions, kind of what we've been talking about. And we have transport as well, which is, you kind of think of it as a very base layer. It's actually what is the base specification from like a bytecode level of actually passing messages. And so what is the benefit of this is if you look at kind of the modular blockchain stack, it was actually able to overcome kind of the inherent trade-offs of blockchains, where in one hand you either had very centralized nodes that were really fast, or on the other hand you had very decentralized nodes that was very slow, right? Like kind of like a Solana versus Ethereum example. But when you add in the modular blockchain thesis and you have rollups, you suddenly have a composite system like Ethereum plus their L2s, which are not only fast, but also decentralized. And so the same thing is happening with the modular interop thesis, and I'm kind of listing some new modular protocols and how they're thinking about it from the interoperability perspective on the screen, where they're actually able to overcome the inherent kind of trade-offs that interoperability protocols have made. And so how is that possible? And so essentially, when you look at the spectrum that I've kind of listed out, and the trade-offs that every kind of solution has made, right? On one hand, you have quick extensibility, but it is less secure because you're relying on some sort of off-chain verification. And on the other hand, you have machines which are not extensible, but are very trustless in that regard. you can essentially modularize this entire stack and swap out pieces of it in order to allow for kind of the solving of this interoperability trade-off and interoperability spectrum that I was talking about. And so some projects doing this are Axelar, kind of comes to mind, but as well as other solutions like Polymer, Earlybird, Layer 0, and Hyperlane. And essentially what they're able to do is swap out their verification layer for all sorts of other mechanisms in order to actually overcome this trade-off. I can talk more about that in a second. But just quickly going back one slide, what is kind of the benefit of modularity? I kind of talked about kind of the best benefits, which is you're actually destroying or you're kind of regarding moots the trade-offs that I was talking about previously that every other monolithic solution has kind of provided. But there's there's an array of other benefits that we see for kind of the ability to modularize the interoperability stack. And so one of them is developer choice. You're able to actually provide kind of different authentication mechanisms based on the use case. Talk more about that in a second. Future proofing, because you're modularizing, you can start swapping out different components that are more optimized or more technologies that are currently in R&D but will kind of evolve and mature and eventually be hardened in the future that you can develop, something like a ZK snark. And you can also mix and match kind of a combination of verification mechanisms in order for maximum flexibility and security. And so I was kind of alluding to what does it actually mean in order to be a modular stack. And so I think the most concrete way in which I can show you guys what a modular kind of interoperability stack looks like is with examples. And so I think the most popular way in which interoperability protocols are able to modularize themselves is actually by swapping out the verification layer. And so if we go back previously again, you could see that it's the app layer, the verification layer, and then the transport layer that kind of contribute to the three different jobs that an interoperability protocol does. And what essentially we're double clicking into is actually the verification and various implementations that other interoperability protocols are deploying in order to be modular on the verification sense. And so on the first piece, you have something that we call app configured. And so this is something that router protocol and layer 0 are doing. Essentially, they're giving kind of the choice up to application developers in order to assess what the verification needs to be. And so in this case for router, what they're doing is they have their own app chain in which they have validation of messages, but you can actually augment those validators with an app-specified off-chain validator as well. And so that's something that's a heightened amount of security for the router use case. And in the layer 0 use case, I think that famously what they're trying to say is every application is able to actually pick their own Oracle relayer pairwise connection. And so different applications can trust different oracles and relayers in kind of their permissionless vision. And so that's kind of a configurable way to do verification. I think the most popular way that we're seeing kind of interoperability, modular interoperability stacks actually looking into modularizing the verification layer is with bespoke solutions. And so this is something where Axelar is coming in, where I know they've been having discussions on how do you actually allow for various verification mechanisms, but also kind of keep the overlying system very similar. And this is something that Seller, Hyperlane, and Earlybird are also doing. And so what this looks like concretely is essentially they're offering different modules within their interoperability solution, and they have different choices of what developers can want to use. And so they can have a choice in which for certain use cases, you can have a multi-signature wallet, something that is very extensible and very quick to adopt. So something that is ideally low value, so Web3 social or NFT use cases kind of come to mind. Kind of the middle area is using optimistic verification. And so something that probably is less, more important than an NFT use case from a value perspective and doesn't necessarily need as much latency or as much finality or quickness to transaction completion in order to do so. And so, this is something that is probably like a low financial transaction. And then lastly, they're able to slide in ZK snarks as well as some form of, this kind of hybrid off-chain, on-chain verification for kind of more trustlessness into the stack. And so this is something that is more kind of suitable for large kind of financial transactions. And so that's kind of the most popular kind of adoption I've seen of a modular verification stack for interoperability protocols. And then lastly, we have something that I call outsourced, where these interoperability protocols aren't even using their own verification layer. And so famously, that's being done by Hop v2 and Connect's Amarok, where essentially they're a liquidity layer that relies on the verification of canonical bridges. And so they can facilitate L2 to L2 swaps just using the canonical bridges. They don't have their own verification layer, which I think is kind of the future. I'm at time, but thank you guys for allowing me to explain something I'm very passionate about. If you have any questions, you can find me after this talk, or you can follow me on Twitter. Thank you.